Welcome to the course on medical biomaterials. We will continue with the mechanical properties that a biomaterial should have, especially when the material is going to face stress either in the form of elongation or compression or shear forces. Okay. Then we need to consider all these mechanical properties. We talked about most important property which is called the stress strain relationship. Okay. They are all connected by something called the Hooke's law, where on the left hand side we have the shear stress and on the right hand side we have the shear strain. So, they are connected by a term called Young's modulus or modulus of elasticity. Okay. So, the shear stress is given by force that is acting on the material divided by the area. Okay. It could be elongation force or it could be a compressible force, and the strain is given by the change in the length divided by original length. So, as you can see, elongation will not have any units, whereas the stress will have units of force divided by area. So, we may have say Newton divided by millimeter square or meter square or centimeter square. So, if you look at the graph that connects the stress or the strain, stress on the y axis, strain on the x axis, you may have the elastic region where the material will follow the Hooke's law, and the slope of this line will be the modulus of elasticity or Young's modulus, and after that it enters the plastic region and finally it breaks. Okay. That is called the yield strength. Okay. So, this may be for steel, whereas aluminum will have a lesser Young's modulus. Okay. So, the slope of this graph will be much lower, and then it will have a very large plastic region because aluminum keeps expanding as you keep pulling it, whereas in the plastic region the material will not come back to its original length even if you remove the force, whereas ceramic, if you look here, at certain value of stress force it will just snap. So, it will not go through the plastic region at all. That is the big problem about ceramics. They have very poor tensile force. They cannot take much tensile force here, it will just break. So, if you have places where you need to have a tension, like if you have joints where there is a tensile forces acting on, or there is a compressive forces especially in the foot region or in the leg, then ceramic is not a good material to use at because they do not go into this elastic and plastic type of deformation as steel or aluminum can do that. So, we also looked at a problem which tells you how to calculate stress, strain, modulus of elasticity and so on actually. Okay. Another important term is called the Poisson's ratio. Poisson's ratio, suppose you have a rod and you are pulling the rod by applying forces on either direction, then obviously there will be a strain, that means there will be an elongation of the rod, and simultaneously in the other direction, the z direction also there will be some change. Okay, because of the elongation. That ratio is called the Poisson's ratio. Okay. So, when I pull the rod, there will be an elongation, there will be an increase in its length, simultaneously in a perpendicular direction there will be a decrease in the diameter. Okay. So, that ratio is called the Poisson's ratio, and there is a negative put here because when you have elongation in one direction, possibly there will be a reduction in the dimension in the other direction, okay, in the perpendicular direction. That is why you have a negative term. Poisson's ratio is also very important in medical applications. I will show you some examples of that. Okay. So, Poisson's ratio is also very important for us to know for materials, whether it is metals or whether it is rubber or plastics and so on. Okay. So, this table sort of gives you an approximate idea about what could be the Young's modulus and what is the Poisson's ratio. As you can see, for many rubbers it is 0.4, that means the strain ratio of strains is almost half from each other. If you go to steel, Poisson's ratio is about 0.33, aluminum is 0.34. So, many metals we are talking in terms of 0.3 to 0.4. Okay. And if you look at the Young's modulus, as you can see, steel is very high, 200, whereas aluminum is only 70, copper is about 120 and so on. So, if you go to quartz, you are talking very high Young's modulus, 300 odd, and whereas rubber like material, it has got very low Young's modulus, 3 gigapascals. So, the slope of the stress strain will be very low. As you can see, the oxides, all the ceramics, oxides, 3 alumina, quartz, okay, magnesium oxide, they are all quite high, okay, when compared to say aluminum, copper, gold and lead, like that. Okay, let us look at a problem. I have a rubber drain tube, okay, it has got a Poisson's ratio of about 0.4, the diameter of the tube is 8 mm and the length is 25 mm. Okay, there is a force applied on it, a force of 100 Newton to pull it out. So, when you do that, there is an extension of 0.02 mm between this. Calculate the normal stress, normal strain, Young's modulus. What is the decrease in the diameter when you pull, because as I said, the Poisson's ratio gives you a ratio of difference in the changes in the dimensions in 2 perpendicular directions. Okay. So, Poisson's ratio is epsilon x by epsilon z 0.4 as given here. So, there will be a negative term here. Okay. And now, let us calculate normal stress, that is very simple, force by area, normal strain, increase in length divided by original length. Okay. Young's modulus is the ratio of stress by strain. Okay. So, the tube diameter is 8 mm square. So, area is pi d square by 4. So, 50.2 mm square, force is 100 Newton. So, force by area gives you the stress. So, this 100 divided by 50, we get about 1.9 Newton per millimeter square. Now, the strain is delta L by L, delta L is 0.02, 25. So, when I divide, it becomes 0.0008. Young's modulus, stress by strain. Okay. So, we get 2487 Newton per millimeter square. Now, the Poisson's ratio minus epsilon x divided by epsilon z. So, there has to be a minus term here, okay, because when it gets extended in one direction, it gets shortened in another direction. Okay. So, which is given by 0.4. Okay. So, I know epsilon x, okay, that is 0.0008. Okay. So, in the other direction it will be 0.002 because you are multiplying by, okay, you are dividing by 0.4, okay, because Ex divided by Ez is equal to Poisson's ratio. So, Ez divided is given by Ex divided by the Poisson's ratio, that is why you get 0.002. Okay. So, the tube diameter is 8 mm. So, the change in the tube diameter is 0.002 into 8, 0.016. So, the diameter of the tube gets reduced by 0.016 millimeter. Okay. So, when the tube gets elongated by 0.02 mm, the diameter gets reduced by 0.016. So, if it is a rubber drain tube, it is carrying some body fluids, so diameter gets reduced. So, the chances are the rate of drain can go down. Okay. So, you need to keep that in mind, that is a very interesting situation you may have. Okay. So, the tube is there is a force acting, so it gets elongated, so slight elongation, so there is a slight decrease in the diameter, okay, because of the Poisson's ratio. So, there could be a possible reduction in the flow. So, there could be a possible reduction in flow. So, you need, that is a situation which can happen. Okay. This can become very serious in certain situation. For example, titaniums or stainless steel screws are used in oral surgery, okay, especially for putting in artificial tooth or artificial caps, okay, and so on, okay. Or titanium or stainless steel screws or plates are also put in bone, especially in orthopedic situation. Okay, if these screws face certain tensile force, for example, okay, there could be a small elongation because of the tensile force, as we saw. So conversely, there could be a small contraction in their diameter also because of the Poisson's ratio, because for metals the Poisson's ratio is almost 0.4. So if there is a contraction, okay, so you may have a situation like this, okay. So there is a contraction, so a small gap could be created, whether it is in dentin in the oral cavity region or whether it is in the bone, there could be a small gap created which could lead to bacterial colonization, bacterial infection and so on. So because of this change happening in the dimensions as represented by Poisson's ratio, one could have situations like that. So in the tooth region, so when you have metals and the metals undergo tension, there could be a small gap created over a period of time, which could be source for accumulation of bacteria. Same thing can happen in the bone region also. Okay, so these are some issues that can happen in realistic situation. Okay, just like tensile forces acting in a longitudinal direction, we could also have shear forces acting on material. Okay, this is very common, especially teeth. Teeth when they come in contact, there is a lot of shear that is happening. So the surfaces of the tooth gets sort of okay, blunted because of this, and again you can have something called shear stress, which is given by force, okay, and the area that is in contact. Okay, shear stress results from a force couple. So there is a suppose I have lower jaw and lower teeth and upper jaw upper teeth. So when they come in contact with each other, it is not exactly meeting each other, but because there could be a slight displacement in the jaws, there will always be possibility of shear forces acting on the teeth. Okay. So there again when there is a shear forces which is sort of parallel to the surface, there could be a small displacement that is called delta x, and this could be the length. So the shear strain could be delta x by L. Okay. So you see the how to calculate shear strain here. Because of the shear stress, the surface gets displaced, so displaced from its original place to a new place, so that difference is delta x. So the length is L, so delta x by L is the shear strain. Okay. So delta x by L is the shear strain. Okay. This is also equal to tan theta, okay, if we look at trigonometry or geometry. So the shear modulus is given by shear stress, that is force by area, and the shear strain is the delta x, that is the displacement divided by the length actually. So materials will have different shear modulus, just like Young's modulus, shear modulus also could be different. As you can see here, for many of these material, shear modulus is much lesser. Shear modulus happens because of two forces, one force happening parallel to the surface on the top, and correspondingly there is another force in the opposite direction happening again parallel. Okay, so it is like rubbing, and that displaces the material. Okay. So these are some values of shear modulus for some material. As you can see, shear or rigidity modulus, as it is called, is lesser than Young's modulus. As you can see here, these numbers as against these numbers. Okay. So Young's modulus for materials are much higher than the shear modulus or rigidity modulus here. Okay, let us look at a small problem. Calculate the force needed to chop off a metal part of 5 millimeter thick and 0.8 mm wide. Okay. So, it has got 5 millimeter thick and 0.8 mm wide. The ultimate shear stress is 50 megapascals. What is the force required? Okay, how do you calculate this? Area is equal to its rectangular cross section. Okay, so 0.8 into 5, that is 4 millimeter square. Shear stress is given by 50. Okay, megapascal, 1 megapascal is 1 Newton per millimeter square, so it is 50. Okay, so shear stress is a force by area. Okay, the force is equal to area in the stress. So, shear stress is 50, area is 4, so we multiply, we get 200, that is the force required for 200 Newton, you understand. So, area is 5 into 0.8 meter square, shear stress is 50. Okay, I have just converted this megapascal into Newton per millimeter square. Okay, then shear stress is force by area. Okay, so force is equal to area into shear stress. So, we multiply 50 into 4. So, we require 200 Newton force to chop off this material. Okay, because 1 megapascal is equal to 1 Newton per millimeter square. So, you see, you need to understand all this conversion factor, Newton to megapascal, Newton to gigapascal per and millimeter square and so on actually. So, you need to have good knowledge about these conversion factors. Okay, then there is something called bulk modulus. Okay, bulk modulus is uniform compression of material. Okay, because as a pressure. So, suppose if a material is dipped inside a vessel containing say fluid acting with the certain pressure. So, the material is undergoing a compression in all direction. Okay. So, there is a bulk stress and there is a bulk strain. So, here volume comes into the picture, change in the volume divided by original volume is called the bulk strain, and the shear stress is nothing but pressure. Okay, because force by area is again pressure, if you remember from your school days. Okay. So, the bulk strain is change in the volume divided by original volume. Okay. This is called the bulk modulus. These are some bulk modulus data for different materials. Okay, you can see here. So, this type of forces come into play if especially when the forces are acting in all the directions on the material, so that the material there is a change in the volume of the material, not change in a linear direction, but change in volume, because volume is complete in all directions. Okay. So, in that sort of situation, Young's modulus we put change in the length divided by original length, whereas bulk modulus we put change in the volume divided by the original volume. Okay. Let us look at a problem. This problem is adapted from this reference. Yes, solid spherical implant immersed in a liquid, so that the hydrostatic pressure is 0.1 gigapascal. This pressure causes a contraction of 1% in the diameter of the sphere. Find the bulk modulus. Okay, so the there is a pressure given here, there is a change in the volume, pressure causes a contraction of 1% in the diameter of the sphere. So, we need to calculate what is the change in the volume. So, the change in the diameter is 1%, so we need to calculate change in the volume. So, it is little bit tricky, not too much tricky. Okay, let us look at it. Suppose d is the old diameter, d minus delta is the new diameter, because the material has contracted. So, that is why I am subtracting V is the volume. So, old volume is 4 by 3 pi r cube. You remember in your school you must have studied. So, instead of r we put d by 2, that is the old. For a new volume we put 4 by 3 pi d minus delta by 2 cube. Okay. So, change delta V by V is given by V new minus V old by V old. So, we need to take this, subtract this and divide it by the V. Okay. So, when we do that, we get d minus delta q minus d cube divided by d cube, all these 4 by 3 pi has disappeared, they get cancelled. So, d minus d whole cube, if you remember, you must have studied in your school again, d cube minus 3d square delta plus 3d delta square minus d cube, there is a d cube outside. So, we can cancel these 2 and then we divide by d, so it becomes minus 3 okay, delta by delta cube okay. And then you have minus 3 delta by d, that is because of this term okay, and this one is minus 3 delta by delta whole square okay. These 2 gets cancelled, so we have like this. You understand how you got this? So, you have delta by d whole cube, then delta by d whole square and then delta by d, this comes here, these 2 gets cancelled okay. Now, we can ignore these 2 because delta itself is going to be very small. So, the delta square or delta cube can be ignored. So, we will just take this. So, delta v by v is given by minus 3 delta by d, delta is 0.01% okay. So, delta v by v is given by minus 0.03. So, what is the formula? The modulus, bulk modulus is given by pressure divided by minus delta v by v, which is given by minus 0.3 and pressure is 0.1 gigapascal. So, 0.1 divided by 0.03 okay. So, this becomes okay 10 by 3, which is 3.33 gigapascal okay. So, where is this 3.33? As you can see, some of the polystyrene or vulcanized rubber can have a bulk modulus of in that order. So, if I take a rubber material and it is immersed in a solution which is giving you a pressure of 0.1 gigapascal okay. So, there could be a contraction in the diameter of the order of 1%. Okay. So, it is an interesting problem which tells you about the overall change in the material dimension. So, originally we saw Young's modulus where we are talking about change in the linear dimension, then we saw the shear modulus where because of the shear forces the material gets pushed or moved. Then we talked about the bulk modulus where the material dimensions are changed in the overall okay. So, all these are very relevant in implants and devices, you have to keep that in mind okay. So, there are different types of materials which one faces in real life situation, especially in the area of biomaterial, because like ceramic I said is a brittle, it does not have a plastic deformation. Stainless steel goes into both elastic and a plastic. If you take polyethylene type of material, they have very low Young's modulus. So, their graphs will be, the stress strain graphs will be of lower dimension okay. So, the different types of materials are possible and this is what this picture tells us. Look at this is a rigid, strong, tough and ductile material. So, because we have a good elastic region and plastic region is also there okay. If you look here, we are having a flexible and ductile region because the graph the increase in the elastic region is not as good as this okay. Now, see, it is a brittle material okay, it is a rigid strong, but it is a brittle material. Look at this D, it is not as big as this. So, rigid weak brittle material okay. If you look at E, flexible weak and brittle material, and if you look at F, flexible and resistant material. So, what is this? We are introducing a lot of terms like brittle, that means materials which fails without plastic deformation, okay, like this, especially ceramics, aluminum oxide, hydroxyapatite. Tough material are materials which energy absorbed before fracture, okay, like this, before fracture is actual breaking, but it is able to go like this, that is why we call this as tough material. Then there is another term which I am going to introduce, that is called creep. So, creep is, suppose we have a constant load, okay, especially you have implants inside the leg and there is a constant load acting on it, okay. So, in such situation, because it slowly starts deforming, permanent deformation under constant load, okay, and it is a time dependent. So, as time progresses, the material slowly starts deforming under constant load, and this deformation is called, is a permanent, and this is a progressive plastic deformation, okay. It does not happen for materials like stainless steel, where the permanently it gets deformed at constant load, okay. But many biomaterials, many biological materials, not biomaterials, biological materials undergo this type of creep, that means a time dependent permanent deformation under constant load. We will talk about those in more detail, okay. So, once again to recollect, okay, ceramic, it goes up and it snaps, okay. So, it is a brittle material, whereas metal, stainless steel, it will go up and then it will absorb the energy, it is ductile and deformation takes later, whereas polymers have very low elastic region, it will have a very large plastic region, okay. So, once just for recap as such. If you look at stress strain curves, and if you take an elastic material, once the load is removed, it will come back, okay, especially in the elastic material, okay. So, it will follow the same straight line, whereas if it is an elastic plastic material, it will come back, but it will come back through a different path, okay. Whereas if you take a plastic material, okay, it will have this type of graph, okay. So, the slopes are different, the way it is going up, the way it is coming down, and there is something where it goes like this, something like a hysteresis, and this is called a viscoelastic material, okay. So, if you have a stress strain graph where it follows the same linear when it is going up or when it is going down, okay, when I keep removing the stress or force, it comes back in the same way, we call it an elastic material. Whereas if it comes back but it follows something like this, a hysteresis, okay, then it is called a viscoelastic material. Whereas if the material goes up as you increase the forces, but then as you decrease the forces, it comes through a different pathway, okay, but parallel but different, that is called so we have a elastic plastic material. So, we can have elastic material, elastic plastic material, and viscoelastic material, okay. All these are possible in real life, especially if you look at different types of polymers, they all will undergo this type of polymers, rubbers, silicones, they all undergo this type of behavior, okay. Okay. So, all biological tissues are viscoelastic in nature. So, if you have the stress versus strain graph here, okay, with time these strain rate, okay, they will start behaving in a different way, okay. So, they will not only depend on the strain, but also on the strain rate. So, the stress and strain are related not only with respect to the strain, but also on the strain rate. So, stress is not only a function of strain, but it also a function of strain rate. That means the the time comes into the picture. Okay. I mean all the biological tissues are viscoelastic in nature, and we will spend more time in the next class. I would like to acknowledge these websites from which some of those figures are taken up. Okay. Thank you very much for your time.